Can you guys hear me?
Yes, we can.
Right. All right, let's begin. We are continuing our series of lectures on recurrent networks. Specifically, we're going to be talking about sequence-to-sequence networks. We also spoke about sequence-to-sequence networks last week. So what was special about the kind of sequence-to-sequence problems we dealt with in the previous week? Anybody remember that? That there was some restriction we had on the kind of transformations that could be performed. Does anyone remember? They were order aligned, right? So here's what the sequence-to-sequence problem is. A sequence of symbols x1 through xn goes in. A different sequence, y1 through ym, comes out. And speech recognition is an example where speech goes in, word sequence comes out. Machine translation, a word sequence goes in, a different word sequence comes out. Dialogue systems, a user statement comes in, a system response comes out. All of these are sequence-to-sequence transduction problems. I mean, who would have thought that a dialogue system is basically just a little mathematical function which converts one sequence to the other? That's exactly what it is. And in general, over here, the number of symbols in the input sequence need not be the same as the number of symbols in the output sequence, and no synchrony may be assumed. So we saw two kinds of sequence-to-sequence problems. The first was speech recognition as an example, where there was an order correspondence between the input and the output. The portion of the input that corresponded to the first output symbol came before the portion of the input that corresponded to the second output symbol. So the order in which the outputs happened had a corresponding order to the inputs. In the more general case, you don't have this. For example, in machine translation, you say the input is I ate an apple. You try to translate it to German. And the output is ich habe einen Apfel gegessen. So then here the ich, of course, corresponds to I, but ate corresponds to habe and gegessen. It's split, and so on. And in fact, if you had a dialogue system and the input was my screen is blank, and the output is please check if your computer is plugged in, there's no real visible apparent word level or symbol level correspondence. So we've already dealt with this problem where you have order correspondence. We're going to be talking about this kind of problem today where you do not have order correspondence. So this is the kind of problem we have where the input and output may not have order correspondence. Is the difference between the two problems clear to you guys? Just please mark yes or no. Thumbs up. Okay. So before I continue, I'm going to go through a brief detour, right? And we're going to be talking about language modeling. So we're talking about recurrent networks. We're all very familiar with language models, but then, what exactly is language modeling? So here's a little bit of a piece of code from some open source project. Which open source project is it? Well, you wouldn't have to look very hard to realize that this is not from any open source project at all. It's just some randomly generated code by a language model. And look at the surprising thing about it. This was a program It was a recurrent neural network, a very simple recurrent neural network with, I think, 2 or 3 layers of LSTMs that was trained on the Linux source code. And then it was run in generation mode. And look at how perfectly it learned the structure of programs. So every open brace is got a corresponding curly brace, corresponding close brace. Open parentheses have corresponding close parentheses, and what comes between the two is perfectly consistent with parentheses, right? Here's an if block. It ends with an else and an else block, and so on, right? So if you look down the code, it's perfectly clean code. It just doesn't think it's kind of garbage, but still. That's because this is a very trivial language model. So here again, as a simple recurrent neural network, which was trained on Wikipedia text. Actually, this was trained on mathematical papers and just asked to generate stuff. And it generates what appears to be perfectly plausible math, complete with pictures. It actually generates it in LaTeX. With a little bit of tweaking, you can compile the LaTeX, and this is what comes out. Or here's something that was just trained on Wikipedia text and nothing else. Not a very large amount of Wikipedia text. So naturalism and decision for the majority of the Arab countries, capitalized was grounded by the Irish language. It's garbage, but it looks very plausible, right? So all of these were examples generated blindly by a very simple recurrent neural network, a few LSTM layers. The example can be found on Andre Karpathy's GitHub page. These days, of course, you get something far fancier than what he did in 2015. But the point was, I'm trying to make here, is that the complexity of the model that is able to do these really fancy things is not very high. It's basically a couple of layers of an LSTM. So neural networks, even simple neural networks, are very, very powerful at modeling language. And of course, ChatGPT is so much more powerful, right? So what do we mean by modeling language, right? That's what we're going to do a brief detour on, modeling language using recurrent neural networks. And more generally, we're going to talk about language models and embeddings. So is anyone here willing to take a stab at telling me what a language model is? What does it do? Anyone? What is a language model? Anybody? Okay. Nobody wants to. Yes, probability of next words. Next opens probability. Okay. I have a bunch of things. Mathematical representations of words, that's valid. Probability of the next word given the previous words, that's also valid. Represents syntax, hopefully, but that's also perfectly valid. All of these are perfectly good descriptions of what a language model is. But from our example, from our perspective, the definition given by Pierre over here, language models generate text in human language. That's probably the closest one. What exactly is a language model? A language model models the probability distribution of symbol sequences in the language. And if the symbols are, or tokens are words, then the probability of word sequences. Now, if I just gave you a random sequence of words, you could take one look at it and tell me it's garbage, right? In general, some word sequences are much more likely than other word sequences. And these are word sequences, for a word sequence to be likely, it should have proper syntax, it should have proper semantics, it must mean something. It's very unlikely for people to go about spewing completely nonsensical sentences, right? So, in other words, you can think of the language as a probability distribution over word sequences, where some word sequences are very highly likely and others are less likely. Does that make sense? So basically, that's what real language really is. I mean, there's nothing stopping you from going about, saying guna gugu ha, habali ha, or whatever nonsense, right? But you don't. The odds of coming up with encountering something completely nonsensical are very small. On the other hand, pretty much everything that you encounter in real life makes sense and it's trying to communicate something. So different word sequences have different probabilities. And so that's what a language model actually tries to model, the probability distribution of sentences in the language. And if you had such a probability distribution, you could do various things. If I gave you a sentence, a token sequence, you could compute the probability of this token sequence. I could also use this in generative mode to generate sequences, basically to draw samples from the distribution of word sequences, or from the probability distribution of word sequences. And if you drew samples from it, and if your language model was accurately capturing the probability distributions of word sequences in real language, then this randomly drawn sequence is probably going to be a pretty valid sentence, right? So this is what you could do if you had a decent language model. And in fact, a whole lot of research has gone in over the past decade into coming up with excellent language models which do a better and better job of modeling the probability distribution of symbol sequences in the language. So, you with me so far? Is this making sense? Because pretty much everything that you see that's related to AI these days, you see this as modeling language. In fact, that's what it is. It's that different languages have different probability distributions. Math has, if you consider the language of math, then you're unlikely to encounter Shakespeare in a mathematical textbook, but you will encounter symbol sequences, which are theorems. So that has a probability distributions over simple sequences. That's very different distribution than if you looked at the probability distribution of word sequences in Shakespeare. But in each case, you have a language. In a language, every possible symbol sequence has a probability. Some have very low probability, some have high probability, and capturing this probability distribution well is what language modeling is all about. So basically, you want to compute the probability distribution of symbol sequences. This is the actual target. But the way we typically do it is by using Bayes' rule. If I have some word sequence, W1, W2, W3, W4, and so on, the way we would do it is to decompose it. This is the probability of W1 times the probability of W2 given W1 times the probability of W3 given W1 and W2, and so on. And so as it turns out that if you're able to compute these probabilities, the probability of the next word perfectly, in the process, you've actually also managed to capture the probability distribution of word sequences in the language, which is why very often we think of language modeling as the problem of predicting the probability of the next token, the next word, or the next symbol. But that is simply a step towards computing the probabilities of entire sequences of words. So again, language models generally perform next symbol prediction, always predicting the next symbol given all previous symbols. But never forget, they actually model the probability of entire sequences, of sentences, of paragraphs, of books. So in the universe of all possible books, which are basically long word symbol sequences, why do some occur and others not? Some are more probable and others are not. And capturing this probability distribution is also modeling language. So given this, we can still focus on this business of predicting the probability of the next token. And so there you would have something like this. I gave you this sequence, 4 7 years. And I asked you, what is the next word? What would you say it was? Anyone? What typically comes after 4 7 years? Ago, right? This was from the Gettysburg Address. And Abraham Lincoln, the next one would be N. So this, not everything was possible immediately after this sequence. So there was this conditional probability where seeing all of this immediately gave you a strong idea of what could follow. Learning this, having the ability to compute this do what you guys just did. Compute the probability of the next symbol in the sequence given the past. That is how we are going to approach language modeling. Again, keeping in mind that the eventual objective is to compute the probabilities of entire symbol sequences. So for this, of course, you got tokens, you got words, you got symbols, which are in language. And our models are not working on language. They're working on mathematical representations. And so the first thing we're going to do is to convert these things to one-hot vectors so that you can feed it to a model. So you might have you might pre-specify a vocabulary of some n words and some fixed, say, lexical order or n symbols. And then each of these is going to be represented by an n-dimensional vector with n minus 1 zeros and a single one in the which occurs in the lexical position of that symbol in your original ordered arrangement. So here, for example, aardvark is going to have a 1 in the second position because aardvark is the second word in our lexicon, in our arranged lexicon. Aaron would have a 1 in the third position. So you could do this with words, you could do this with, word fragments, with characters. If you want to model the probability distribution of character sequences, the vocabulary is just about 100 characters. So every character is going to become a one-hot vector of some 100 dimensions. And so once you're past all of this, the problem is now predicting the next symbol in the sequence. So you're given W0 through Wn minus 1, and you must predict Wn. This is done through some function where all of these are represented as one-hot vectors. So if I want to illustrate it pictorially, this is what it would look like. W0 through Wn minus 1, all of these being one-hot vectors, go into your function f, which generates a one-hot vector, which is Wn. So is this figure making sense? The one to the right? Okay, so what could a problem be with, how would the one-hot approach work? Words, misspellings, things that are not in the lexicon are not going to be representable, period, right? They will never, they can neither go in nor come out. W here is, these are just words, not weights. Okay, so word sequence. Now, what would be an issue with a representation of this kind? Very, very sparse, right? All the inputs are very high dimensional and very sparse. If you're working with words and in English, then in English you need about 100,000 words to get most of the language, which means that every single word is going to be represented by 100,000 dimensional vector, of which only one element is non-zero. If you were working with Russian, you need 400,000 words. So each vector is going to be a 400,000 dimensional vector where all but one dimension is zero. So why do we even bother using such a sparse, ridiculous representation? Why don't we use other vectors? Why couldn't I, for example, if I've got 1,000 words in my vocabulary, then log to the base 2 of 1,000 is what? 20? So in principle, I could just be using a 20-dimensional vector to represent all words. Could I not? Yes or no? So why don't we use that? Why don't we use that, right? So here's why, right? First, why one-hot representations? Because a one-hot representation makes no assumptions about the relative importance of words. If you began giving them other values, then some vectors, if you read the bit string out, that's going to represent a number, and some numbers will be larger than others. So you're implicitly assigning some kind of an importance to the words. This word is a big number, so it's more important than this other word, which is a small number. Like it or not, that implication will exist. In a one-hot representation, every vector is exactly the same length. In an n dimension, if you have n vocabulary, and a vocabulary of n symbols, and all the vectors live on the corners of a n-dimensional cube. Specifically, you're just using the n-axis, right? So if I have a vocabulary of 3 words, then the 3 vectors are 1, 0, 0, 0, 1, 0, and 1, 0, 0, 1. Observe how all 3 vectors are length 1. But then here's the other thing. What is the distance between any 2 vectors in a one-hot representation? The distance between any 2 vectors. So, and what is that distance? Between any 2 vectors in a one-hot square root of 2, right? So basically, you're not assuming a priori that word A is closer to word B than it is to word C. In the absence of other information, it is improper for us to make this assumption. And so a one-hot representation has this property that it makes no assumption about the importance of words. They're all equally long. And it makes no assumption about how close words are to one another because they're all equidistant from one another. That's why we use one-hot representations. But then this comes at a cost. It's extremely sparse. Look at this. If I have 100,000 dimensional vector, 100,000 words, in this 100,000 dimensional space, I am using only 100,000 points. Look at it this way. If an entire plane, go down to just a plane of two axes. If I told you I gave you an infinitely sized sheet of paper, but then the only 2 things I'm going to use on this infinitely sized sheet of paper are these 2 points. Is that good use of the space? Would you call that good use? It's horrible, right? Because think about it. This 100 represents a word. If I just go off away from it by a small epsilon and I go to 1 epsilon delta, this is a meaningless thing. It has no interpretation at all. So it's the total volume that you're using from the space is 0 because each point is just a 0. And the density, if you assume that you're only considering this unit cube, the density is going to be, this volume of the cube is 2 raised to n. The number of points is just n. And so the density is going to be of the order n over, r raised to n, where r is the size of the edge. And this is going to be very low. Is this making sense? The business of the density and the fact that a small perturbation has no meaning. Yes, no, it makes sense, right? And so we can't do anything about this guy. The fact that it's occupying 0 volume cannot be fixed. It's a problem with machine learning, but we can try to increase the density. And the way we will do it is to project this one hot vector into a subspace by multiplying it by some matrix P. This P is a projection matrix, which zaps all of these points down onto a lower dimensional hyperplane. And if you do this properly, then, and if this P is properly learned, then both the absolute values of these points and the distances between them will begin to make sense. And so we leave the business of figuring out the relative importance of words and the relationship between words to a learning problem, and that is specifically the problem of learning this projection. So how do we do it? First, we assume that every word is first going to be projected down, like so. And so you're going to be projecting, meaning every one hot vector is going to be passed through this projection matrix, and the projected down words are not going to this function. The function predicts words. So the function is not going to be predicting the projected downward. The prediction is still one hot because this is a classification problem, but the projections apply to the input. And so, of course, we know that a projection matrix is just a linear layer. So it's like applying a linear layer to every one of these one hot vectors before the same linear layer to each of these vectors before passing them into the function. So you can still now view this entire prediction model, which is a language model, as a network with identical subnets because these guys are all identical. It's a shared parameter network. This making sense? Yes, no? Okay. Right. So now having set this up, let's look at what we can do. First, if I'm predicting the nth word based on the previous n minus 1 word, what kind of a model is that? Can anybody tell me what kind of a model is that? Yes, but what kind? An RNN? It's a time series. I'm predicting the current word based only on the previous n minus 1. What kind of a model is that? Is it recurrent? It's a TDNN, right? Yes. So here's what it is. I'm predicting the TDNN model. You're predicting each word based on the past n words. This was originally proposed like this in this paper, Benji et al. In 2003, where each of the words is first passed through the projection layer. And then you just have a simple TDNN model where it's trying to predict the next word in the sequence by looking at the previous n words. So you don't need explicit labels because, the label at time t is the input at time t plus 1. Nevertheless, this is just a TDNN model. This making sense? And this is just TDNN. Okay. So this is not recurrent. Okay, Miguel, if it were recurrent, how many past words would it be considered? Infinite. If it's finite, is it recurrent when it's just a short window? It's not, right? So this is a convolutional network. This is a TDNN. So you can have other kinds of models. When people figured that you could do this business of trying to find out the best projection matrix became a bit of a cottage industry. So we had these other models. This was the so-called soft bag of words, where you were going to predict a word based on neighbors on both sides, or the skipgrams, where a word was used to predict the neighbors on both sides, and various other things. Regardless, when you did it, you ended up getting very nice results of this kind. So once you project it down in the lower dimensional space, you would often find relationships like this. See the relationship, the vector distance between China and Beijing. It's very similar to the vector that connects Russia to Moscow, Japan to Tokyo, Poland to Warsaw, right? So the relationships between words seem to be the arrangement of words seem to capture semantic relationships. This is clearly a country capital relationship. And they had other examples where they showed that king plus woman minus man gave you queen, because the vector that connected man to woman was the same as the vector that connected king to queen. So very nice. And so that's what these embeddings do. So these things, these projected down vectors that we get after projecting the one hot down vector down with P is called an embedding. And that's what these embeddings do. So that leads us to our first poll. Let me release the first poll. Can you see the poll? Okay, 10 seconds, guys. Aha, what is the meaning of the one-eyed owl? Tell me at the end of the class. Okay, let me terminate this poll. I'll give you extra credit if you tell me what the meaning of the one-eyed owl. Okay, here's what you think. That all of you guys think these are your guesses. So is this first statement true? The distance between any two non-identical one-hot vectors is the same. True or false? The first one. True, right? Second one, words are represented as one-hot embeddings because these do not impose any a priori assumption about which words are closer than others. True or false? True. Word embeddings derived from language models are lower dimensional real valued representations where the distance is a meaningful representation of the closeness to a false. Low dimensional embeddings enable you to find representations for words that were not part of the training vocabulary, true or false. This last one, you can't, that's fixed, right? So the first three are true and the last one is false. Thank you. So here's where we are. Now I could do the same thing with a recurrent model. In the case of the recurrent model, the entire model looks pretty much the same, except now instead of just having a convolutional network, it's going to be it will have a recurrent network. And when I have a recurrent network, at any point, what is the probability distribution being computed? Is it the probability of the word in isolation, or the probability of the word given just the previous word, or the probability of the word given some history of words, or the probability of the word given the entire past? What is being modeled at any time of these four choices when the model is recurrent? So at any point, what is being computed is the probability of the next word given the entire past, right? Perfect. That is the key bit. So if I have this, how can I use this to generate text? I can just take a whole bunch of text. I can train this model where the label at any time is the next word in the sequence. So I don't need external labels. I'm always using the next word in the sequence as the label. And now I can use this to generate more text. I might have some initial text, W1, W2, W3, right? So fourscore and then based on these at time 3, you would get, the model would compute a probability distribution for the next word. And then from this distribution, you could sample a word and then feed that back in. And now you have 4 words going in, and the network is going to compute the probability distribution for the next word from which you can draw a sample and keep doing this until you stop. Now, when do you stop? There are some cases where termination is obvious. For example, if you're generating C code, the moment you see the final curly brace, you know the thing is done, right? In other cases, no. So here, in this one, this was just an RNN trained on the Linux source code. You know that this was the first open brace. So as soon as this guy is done, the code is done. And this was a very nice example. I don't know if I can play this and whether you can hear it. Is getting sound going through to you guys? I guess not. Let me reshare this. Stop share. I'll share this again, this one, but I'll share sound. And so, yeah. This was interesting. Someone just trained a little LSTM on MIDI and used it in generative mode, and it generates perfectly plausible music. This was in 2015, 10 years ago. These days, of course, you can get entire symphonies out of it, right? So these are easy. You know, in the case of programming tech code, you see the final curly brace, you know, it's time to stop. In the case of music, there's no need to stop. You can just keep going on and on and on, right? But more generally, you need to stop. So when do we stop? Do we just keep going on forever? That doesn't make sense. So we need to have some way of indicating this. And so here, we actually like to mark beginnings and ends. A sequence of words by itself does not indicate if it's a complete sentence or not. If I just look at 4 and 8, I don't know if it's the beginning and I don't know if it's the end. So to make it explicit, I'm going to add 2 additional symbols: a start of sequence, a start of sentence marker, and an end of sequence or an end of sentence marker. So here, for example, 4 and 8 has neither an EOS nor an SOS. So this is clearly the middle of a sentence. SOS, 4 and 8. So it means that 4 was the first word in the sentence because it was preceded by a start of sequence marker. So this is the This is a fragment from the start of a sentence. 4 score and 8 EOS. So after 8, you've generated an end of sentence marker. So clearly this is the end of a sentence. SOS 4 score and 8 EOS. So this means that the sentence began at 4 and ended at 8. So this is a full sentence. So these tags make the beginnings and ends very explicit. And for engineering purposes, you may often not have separate SOS and EOS tags and simply have a single tag for both start and the end. Nevertheless, the key thing is that these terminations and initializations must be tagged. And so when I generate text, I can keep drawing stuff and keep producing stuff until I draw an end of sentence marker, or I might have other criteria. Generate no more than 100 symbols, in which case, I'd use this additional criterion to stop. And so the story so far, language models model the probability of word sequences or symbol sequences in the language. This is typically performed in the form of next symbol prediction. Given the symbol sequence W0 through WK, it computes the probability distribution of the next symbol, P of WK plus 1, given W0 through WK. And this could be computed using a recurrent neural network. That's why RNNs. And they can be used to both compute the probability of an entire symbol sequence, or to just conditionally generate or extend symbol sequences given an initial prompt. Both of these can be done. So with that said, here's your second one. Okay, this one's easy. 10 seconds, guys. Okay. I'll terminate the poll here. And here's what you guys thought. What's the answer, guys? Hey, perfect, right? So this is the one. And so now let's return to our problem. This is the problem you're dealing with, where we've already handled the order correspondence. This is the one that we want to deal with. No correspondence between input and output. They may not maintain the order of symbols or even have any kind of immediate apparent relationship between the output and input. What kind of model can deal with this? For this, we've already seen the model. The obvious one is this guy, the delayed sequence to sequence model that we saw a couple of classes ago. This model takes the entire input, and once the entire input has been processed, there's a hidden state computed, and this can be used to generate the entire output. So this model has two parts. The first part processes the input to generate a hidden representation from it. And then the second, so here's the pseudocode for it, right? Just this one. You're going through time. At each time, you're taking in the current input and the previous hidden state to generate the next hidden state. And the hidden state after the final input is the key bit. Once that is computed, then you can use that to generate outputs. Now, what does the code for that look like? Like so, right? Here's the bit which processed the input and generated a final representation. Now for the output, this final representation is going to be the initial hidden representation. And then at each time, you do two things. At each time, you generate a hidden state value itself. And then you also generate the output probability distribution. So because from this guy, when you take in this hidden state, you're computing this one, and from this one, you're computing this as well, right? So you generate the hidden state, current hidden state, and the output probability distribution. But what is the actual output word? The output word is going to be drawn from this output probability distribution. And we keep doing this till the end of sequence marker is produced. But then, so is this making sense so far? It's broken, but is it making sense? What we're doing? Okay. So I have 8 TSS order. But so how is this broken? This business of generating an output word is actually drawing from a distribution, right? So consider this case. Let's say at this word you had a probability distribution computed, which is this one. In one case, the word that you drew from it was the word A. In another case, the word that you drew from it was the word am. Now, if you sample the word A from this, then what is a reason? What kinds of words can follow if the word that you generated here was A? Is the set of words that can follow unrestricted? No, they must start with consonants. On the other hand, if you drew an, what kinds of words could follow? Words starting with vowels, right? Is there anything over here which says that, which informs the model that I drew an A, and so only words with consonants are acceptable over here? Is there anything in this model that does that? So how would you fix this? There isn't, right? So how would you fix it? Right? So the issue here is that changing this output at time t doesn't affect the output at time t+1. If you have drawn it was A versus it was an, the probability that the next word is dark remains the same. And this is because the output at time t does not influence computation at t+1, right? As you guys just mentioned. So what we want to do is to feed the drawn word back as input. And so this is the actual model, not the one to the left, but the one to the right, because this makes more sense, right? And this begins to look like the knots network. Just give me a second, guys. Sorry, guys. I'm also in the middle of a family emergency, so I will get some classes, some phone calls, right? Okay. So I'm assuming that everybody's with me so far. So here's this is what we'll call the simple translation model. The input sequence feeds into this recurrent structure, and the input sequence is terminated by an explicit end of sequence symbol. And then when we encounter this end of sequence symbol, then the hidden representation over here stores all information about the sentence. Subsequently, the second recurrent network uses this hidden activation and a start of sequence marker as an initial symbol, and then proceeds to generate the outputs. And the output at each time becomes the input at the next time. And the output production continues until an end of sequence is produced. So, over here, this guy would go in here as the initial state and the start of sequence marker. That's why you need a start of sequence marker to say initiate generation. And then you generate a word which would go back in, and you keep doing this till you eventually generated an end of sequence marker. And then you know the output is complete. So observe that because things are going back in as input, drawing a different word over here would just mean that the subsequent output is going to be is going to all change. Now, I've drawn a very simple model with just one hidden layer, but keep in mind that this is only for illustration. That hidden layer can be arbitrarily complex. I'm just not, the complexity of the hidden layer is kind of slightly irrelevant to the immediate topic. It's only relevant to the effect that the more complex it is, the more powerful the model gets. But for the purpose of understanding the underlying concepts, we can hide it all under this simple illustration. So this is what I'll use. So here's what the generation looks like over here now. You get the initial hidden state. Your initial input is going to be a start of sequence marker. Then at each time, the current hidden state and the last symbol output are going to be fed in. And then this will result in a new value for the hidden state and an output probability distribution from which the word is generated, right? So again, observe that if I sampled a different word over here, at the next time instant, that guy is going to go in and change the outputs all the way down the line. So this is our simple translation model. The portion that processes the input is called an encoder, and the portion that generates the output is called a decoder. So this is terminology. Now, let's take a slightly more detailed look at how this is done. Firstly, words are all going to be, or tokens are going to be represented as one-hot representations, but they will be compressed to embeddings through a standard projection approach that we saw. And these embedding matrices could be pre-learned, or often they're just learned as part of the model itself. In the rest of my lecture, I'm not going to show these P's. Here, observe that I have different P's for the input and the output because I'm using an example of translation. So this one over here would be the projection matrix that's appropriate for English. This would be the projection matrix that's appropriate for German. But again, there are different ways of setting this up. I'm not going to show these P's. So here now, what does the network actually produce? For that, here, observe. The input has been processed, and then you've given a start of sequence marker. It computes a probability distribution. What is this probability distribution? This is the probability distribution for the next word in the sequence, given everything that has come in so far. That is the input and the start of sequence marker. That's what this distribution is. Is that making sense? Okay, so the symbols over here, this Y0 superscript anything, Y0 superscript word is the probability of the word beer. For example, Y0 beer is the probability of beer given that the input was the sequence and that a start of sequence marker has been initiated. So you would draw some word from this and you feed that in. At the next time, you now have a probability distribution that's being computed. This probability distribution is the probability of words, the next word, given that the input was I ate an apple and that the first word in the output was ish. So it's going to be the probability of O2 given the entire input and O1. That makes sense? Okay, so if I've sampled ish, right, here, that has gone back in. So ish is part of the input that was used to compute this probability, right? So Pierre, I'm going to draw it. I'm going to generate it. So we'll get back to how we got the ish from this distribution. But we got it somehow, okay? So, and then that goes back in. So at each time, what you're really computing is the probability of the next word, given everything until then. So Y subscript K superscript W, this is the output computed for the word W at time K, is this set of values is the probability distribution for the kth word given the input and the first k minus 1 words. So is this making sense? Yeah. The idea, right? So when this goes back in, that's going to go through the projection matrix. So we always have the P, okay? Like I said, I'm not going to actually explicitly show these P's, but these P's are ever present. And so this is how the generation is done. Okay, so here's what the pseudocode does. At each time you have y of t, and you're drawing the next word from this y of t through some magic operation. What is this magic operation? And what's the point behind it? So again, observe. What is the probability distribution of any output sequence, O1, O2, O3, O4, O5, given the input sequence? The probability of an output sequence given the input sequence, I can break it down using Bayes' rule as P of O1 given the input sequence times P of O2 given O1 and the input sequence times P of O3 given O1, O2 and the input sequence, and so on. Right? So this decomposition makes sense to you guys? Okay. And what is P of O1 given the input sequence? That's basically the probability computed for O1 out here, right? What is P of O2 given O1 and the sequence? That's the probability computed for O2 out here. So the probability for any given output sequence is simply the product of the probabilities computed for those symbols in the sequence by the network. To make it more explicit, here's an example. Let's say ish I ate an apple went in. What is the probability of ich weiß nicht was ist? Which is not a correct translation, right? But if you sample stuff, you could well have sampled these too, right? So what is the probability of this? This is going to be the probability of ich weiß nicht was is given I ate an apple is going to be the probability of ish given I ate an apple times the probability of weiß given, this should have been ich weiß nicht was ist, right? Ish I ate an apple times the probability of nicht given ich weiß I ate an apple, and so on. Right? Is this making sense? Over here? Rest of you guys? Okay. And this term here, P ish given I ate an apple, is just simply the y value computed for ish at time 1. And because ish has gone back in here, this term here, P of y's given ish and I ate an apple, is simply the probability computed for y's in this column, and so on. So the probability of this word sequence is the product of the probabilities assigned computed for each of these words in the sequence by the network. Again, is this making sense so far? Yes or no? Okay, I'd like to see 25 thumbs ups because this is where it, I have T4. I'll wait for the 25. I'm still at 15. 20. I need 5 more, guys. Just give me the thumbs up. It's going down rather than up. Oh my good God. All right, I have to continue. All right, so now what is the model really trying to do? And if I'm performing translation given an input, it's trying to obtain the most likely output, right? Yes or no? And so the objective of drawing is to generate a sequence of symbols here such that the probability of that sequence given the input is maximized. In other words, you want to compute the symbol sequence O1 through OL such that the product of the probabilities assigned to O1 through OL is maximized. This making sense? Good one here. Okay. And so this is the objective. So how do I draw words? Remember, the word that is drawn. Okay. Guys. Just bear with me, guys. This doesn't always happen, but I have a minor emergency. Sorry about that. My mom's flown somewhere, but her phone is dead. And my sister is supposed to pick her up, and they're using me to coordinate. Okay. Uh, so, all right. So again, the question is this, right? How can I remember that any word that I drew over here is going to change the future, correct? Yes or no? Okay. So given this, how do I derive words from this probability distribution that maximizes the overall probability of the sequence? Any ideas? How could I do this? Any ideas? How many combinations? Could check every possible combination. How many do you have? Infinite. No, right? So, okay. Is there a better idea than that? That's the correct thing to do. Is there a better idea? So, beam search. Exactly. No, no. So again, let's explain. You guys have the answer, but let's go through what, right? The greedy answer is to select the most probable word at each time. And it's very easy. So basically, I could just say, pick the most likely output at each time. And this, so YT is a probability distribution. I can just do an argmax and I get the next word. Why would this not work? Let's see why, right? I cannot just pick the most likely symbol at each time because that can cause the distribution to be more confused in the future. And choosing a different, less likely word could cause the distribution at the next time to be more peaky, resulting in a more likely output overall. So let's see how. Let's say I have this, maybe I'm performing speech recognition, right? And so the first word drawn was the word he. Then at the next word, the word nose with N-O-S-E and the word nose with knows with K-N-O-W-S. Both sound very similar and have very similar probabilities. But the probability for nose, this object on your face, is slightly higher. So if you pick the nose here greedily because it's more probable, now you get this crazy word sequence, he knows. What kind of a word sequence is he knows? It's not clear. This doesn't sound like proper English. So when the model tries to see what the next word could be, it's confused, and it's going to assign a somewhat flat and low probabilities to all words. So when you draw the third word and factor in the probability for the third word, although nose scored higher than knows, after factoring the third word, the overall probability is not going to be very high. Whereas if you had chosen knows with the K, even though it was slightly less probable than knows, because he knows is a very structured language. If you look into the future for the next word, some words will just stick out, like W2 over here. And so choosing that word is going to give you a higher overall probability for the third word's three-word sequence than in the first case, even though the second word was less likely than the second word here. Is that making sense? This example over here. Okay. And so, but then the problem is you don't really know. You don't have the look ahead, right? You don't know. Here I've given you an example where the confusion occurs immediately, but the confusion could occur anywhere down the line. And so you don't have the look ahead. It's impossible to know a priori, which word leads to the more promising future. So, should we draw nose or knows? Locally, nose looked better, but the nose was better if you looked into the future, right? But then it could be worse, right? Maybe in the very first word, you had a choice of he and thee. and he scored slightly higher, so you chose he, right? That gave you the nose confusion at the next time. And then subsequently you got he knows something. But then if you had chosen the over here, then the choice of nose with the N at the second time would be more reasonable. And it's very likely that when you get to the third word, the overall sequence is more likely. And so the fact this, so the fact that you had to choose the and not he is only becomes evident after some time. And we don't have look ahead, we don't have particles. Now, an alternate solution is to just randomly draw a word from these distributions. And we all know how to draw a sample from a category distribution. Obviously, this is not going to be optimal. This could just be a random sample here. And so random sampling is not guaranteed to give you the most likely output, but strangely, it can sometimes give you more likely outputs than greedy search. But what we really want to do is something slightly different. And before I get to that, we have our third poll. Wait a minute. I should stop sharing this. I'm ending this poll. This is what you guys thought. Okay. First statement, true or false? Second one. Third one. I haven't told you this. Yeah, we're paying attention, right? And yeah, okay. So we see that our choices can get you stuck. Making a poor choice at any time commits us to a poor future, but we cannot know at that time that the choice was poor. So the solution, do not choose, right? Here's what we're going to do. From this distribution, we could have picked any of these words. It's okay. From this distribution, we could have picked any of these words, right? Instead of picking a word, we clone this portion of the network and make one copy of it for every possible word. And then out here, once again, you're going to have a probability distribution over all words. So out from here, I'd make one copy of the network for every possible word, and I'd be feeding all of those guys in. And so I can actually generate the entire tree of possible symbol sequences, word sequences. And then I can compute the probability of any word sequence by simply multiplying the probabilities all along the tree. And then I can pick the highest one. And this is going to be the correct thing to do, right? Do you agree with this? Yes or no? Any responses, guys? Okay. And the problem here, someone mentioned it. What's the problem? What would the problem be with this? Right? For an output vocabulary of size V, after T output steps, you would have forked out V raised to T branches. You're going to run out of compute and memory. It's exponentially branching very, very quickly. So this is not feasible. So how do we deal with this? And many of you gave me an answer. How do we deal with this? The beam, right? So I'm going to prune. at each time. So I generate all of these guys. But at this time, I decide I'm only going to keep the k-best choices. And I keep only the top k. And only these, so in this example, my top k is 2, right? And so the top k is based on the probability of the symbol based on the input. And then I'm going to be making 2 copies of the network, one taking he, the other taking v. At this point, again, the model is going to compute the probabilities for all the words on both branches. And then from across these 2 sets of branches, I'm going to pick the top 2. And the criterion for picking the top 2 is going to be the product of the probability here and the probability here. So here, for example, for nose, I'm going to be choosing the probability of nose given the input and he times the probability of he, that's the input here, given the input. And for this one, for the NOSE nose, this would be the probability of nose given the entire input sequence in the word B times the probability of D given the input. So I'm multiplying all the probabilities down the path to each one of these guys, and then picking the 2 most likely. And those are the only ones that would stay. Now, those 2 can be expanded again. And at this point, again, the network is going to generate our compute probabilities for all words, of which I pick the top 2. But then to choose the top 2, I'm going to be multiplying the probabilities down the entire path, because you really want to pick the word sequence, the 2 word sequences with the highest probabilities. And those are the ones you choose. I know this sounds confusing, so any questions? Or if you don't have, if this made sense, just give me a yes or a thumbs up. Does this make sense? Okay, so this is what we're going to do, right? And we can keep doing this. And so at each time, you're going to use the top k, where the top k is based on the product of probabilities all the way down the path. And you stop when the current most likely path, overall path, ends in an end of sentence marker. It's not enough for one of the top k to have an end of sentence marker. Firstly, once you generate an end of sentence marker, you do not continue generating down from that point on, because that sentence is complete. At any point, you have a bunch of partial hypotheses. If the hypothesis that ends with the end of sentence marker is the highest currently scoring hypothesis, that's the one you're going to output. Of course, this also gives you the ability to generate the n most likely hypotheses instead of just the top 1 hypothesis, and that too you can do. So one of the things, paths cannot continue once you output an EOS. So this thing is never expanded. These are not expanded. And so the paths may be different lengths. And you're going to have to pick the most likely sequence ending in an EOS across all terminating sequences. And that comes with its engineering problems, because this tends to have a bias towards shorter sequences. I have some pseudocode for the beam search. I'll skip it. And this is our final poll. After this poll, I'm going to all right. So, Shrey, you got it. All right. Let's terminate the 4 and 5 seconds. So, here's what you guys thought. And so, first question, true or false? Second one, Is the second one true? Beam search doesn't necessarily pick the most likely hypothesis. To be certain of picking the most likely hypothesis, you'd have to do the entire tree. So this is still an approximation. It's just a better approximation than greedy search, because you're considering more than one hypothesis. That makes sense? Yes, no? Okay. So let me continue, right? And good job, Shrey. So how do we sorry, how do we train the system? We must learn to make predictions appropriately. So given I ate an apple, we must learn to produce a Shaba and an Apfelgegessen, right? And so for this, something interesting. In the forward pass, I'm going to input the source and the target sequences sequentially. Now there's something that in your standard neural network training, an input goes in and you get an output, and this thing is compared to a desired output, and you compute your loss, right? This is what you minimize. So you remember this, right? This one here. Okay. In this case, I'm giving the input, and I also pass the target sequence, because the target sequence is being treated in much the same way as we would for language modeling. Okay. And so you pass the input and the target sequence, and you keep predicting the next word in the target sequence. And at each time, you have the next word, the actual next word in the target sequence as the label. You compute the divergence between the next word in the sequence and the output. And this divergence is the one that is, the derivatives of this divergence are what are passed back to learn the model. Now, did someone observe the difference between how this is trained and how models are normally trained? Did someone observe the difference? Two different data sets? No, in your standard neural network training. So what is the difference? Okay. In your standard network, here's what happened. An input went in, right? An output came out, and then you computed a divergence, right? Is this what is happening over here? What is happening here is something different. The input and the output are going in, and the output is coming out, correct? It's not merely that it's autoregressive. Do you see that this is what is happening here? Is this the same as this? Are these two comparable? Come on, guys. No, right? If you were training this like a proper neural network, what would you do? What would you do? Only the input would go in. And then you just run this thing in autoregressive mode and generate an output. And that output would be compared to this guy, correct? Yes or no? Right. Why don't we do that? Why don't we do that? Because, any guesses? I'll give you 5 seconds. Okay, a few more seconds. Someone, guys. It's not, because if I just fed in the input, imagine what the model is at in the initial stages. In the initial stages, the model is going to be crappy, right? And instead of producing anything close to Ishaba and an Apfelgeges, and it could just produce like a 500-word sequence of gibberish, right? Yes or no? Exactly, but Elvis is right, yeah? Could you compare that to Ishaba and an Apfelgeges, a 500-word sequence of gibberish? No, they are not comparable. You don't even know how to compute the loss. It breaks down, right? Because, you want Ishaba and an Apfelgeges, and this is going to say, good morning, America. I'm going to read you the Gettysburg Address. Or not. It's not even going to be anything that structured. There's no way it's going to be comparable. Whereas, so what we did by feeding the input back in, cheating, this is basically cheating, right? This is what we call teacher forcing, where the desired output is being fed back in, and that makes it possible for us to obtain one-to-one correspondences between the output of the network and the desired output of the network. And then the divergence can be computed. That makes sense? Yes or no, guys? What about the rest? If I have two yeses, can I get 15 yeses? Yes. Some thumbs ups. Okay. So this is not really training in the standard approach. We are doing something different. We are feeding the output in along with the input. It's a bit of cheating. We give it a fancy name. We call it teacher forcing. But that is essential if we want to be able to compute these divergences in a meaningful manner, right? And then once you do that, there are a bunch of engineering tricks that people uh, have tried on this model. Instead of computing divergences everywhere, you could just randomly pick one. So Brian, uh, to, when the model is still in the initial stages, it could just produce a and blah, goo, 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 right? And keep producing this. Can you compare this to Ishaba and Apfelgeges and computer loss, a differentiable loss? Right? Can you do that? So you don't want this, right? By cheating in this manner, you always know what the next target word is. And so you can compute a loss. That's why you do this. Does that make sense, Brian? Okay. And so that's basically what we do. And there's some engineering tricks which I won't get into, but here's the overall training. You're given several training instances of input and output sequences. In the forward pass, you compute the output, but then observe that both X and D are used in the forward pass, unlike in your standard training, where D is the desired output. And then in the backward pass, you compute the divergence and propagate derivatives backwards. So some applications, machine translation. My name is Tom. Misha is a Tom. Speech recognition, speech recording. Outcomes, my name is Tom. Dialogue, I have a problem. How may I help you? All of these can be addressed using this approach. You can even do image captioning. So give me 2 minutes extra, guys. Here's something very interesting. So all of this is done because the input is processed and you get a hidden representation for the entire input in this hidden state. So this in the hidden state should in principle capture the semantics for the input. Does it? Here are some examples that people have that the original author showed by projecting everything down to 2D. So what do these representations look like? John admires Mary. John is in love with Mary. John respects Mary. Mary admires John. Mary is in love with John. Mary respects John. Observe that the three are similarly structured sentences, just that the order of the subject and object have changed, and the two have the same arrangement, right? Male to female is down here. Female to male is down here, up here. I was given a card by her in the program, and in the garden. In the garden, she gave me a card. She gave me a card in the garden. This is just flipping the two. She was given a card by me in the garden. In the garden, I gave her a card. I gave her a card in the garden. Again, you can see that even at the sentence level, it's keeping all of the structure. So it's doing a fantastic job of actually computing structure. So you see this over here? Since I'm out of time, I'll assume you do. They have some examples for machine translation. I'm told they're good. We're going to have to believe it. Here's one that they did for a dialogue system. And if you go through it, it's the machine sounds almost human, right? But then there's something else you can do, right? Now, once you break it up into encoder and decoder, the encoder could be encoding anything. And so this was where the first really good image captioning model came out. The encoder, for the encoder, they used a CNN. And the CNN's output was used to generate sentences. And this first paper on image captioning, the first really good paper on image captioning, basically used this model, where they just replaced the encoder with a CNN and use that to feed the network. And it does a really good job, right? I won't go into the example. We've seen this before. But there's one problem in the decoding. So give me this extra minute because we're going to follow up on this. And that is that if you look at this model here, the entire input, this input is now, the entire input is represented by this one box, and that's fed down the recurrent network into the decoder. So what happens is that this information keeps getting diluted as you go forward. By the time it gets here, this guy is being messed up because of all of the dilution that happens through time. So when this is generating the next word, it's looking at a much weakened version of this representation. Does that make sense? So how do we get around that? A couple of different solutions have been proposed where you say, I'm going to feed this in at every point. And so even for the image captioning, they did that. They did the same thing for video captioning. And they found it works really well. I have some pseudocode. So the story so far is language models model the probability of word sequences in the language, typically through next symbol prediction. This is what the model we saw today is the simple sequence to sequence model for tasks such as machine translation. They're performed using an encoder-decoder model where the encoder extracts a feature representation for the input. And the decoder is actually a conditional language model. The decoder that we saw is no different from the RNN language model we saw initially, except that it gets one more input, and that is from the encoder. So it's a conditional language model that uses this representation to conditionally generate the output sequence. And inference is performed to find the most probable output sequence. And the same mechanism can be used for other conditional generation tasks like image captioning, video captioning, etc. But then here's a problem. The entire input is being represented by this guy. This is being overloaded. We can do better. How? We will see in the next class. So thank you for your patience. I ran a little over. I hurried up at the end. But yes. So Shrey got the answer. I'm hoping to be back in person on the 4th of November. Any questions, folks?